If you've ever tried to run an Abaqus simulation and suddenly it stops with the error "too many attempts made for this increment," this video is for you. Most people try random fixes, changing the time step or restarting the job without actually understanding why this error happens. In this video, I'll explain where this error really comes from and the theory behind it in a very simple way, and exactly how to fix it step by step. Once you understand this, you'll stop guessing and your nonlinear simulations will actually converge. Let's start with the most important thing. This error is not a bug. Abaqus is not broken and in fact is doing its job. The message "too many attempts made for this increment" means only one thing. Abaqus could not converge the current increment even after reducing the increment size multiple times. In other words, Abaqus tried, it failed, it reduced the increment, it tried again, and after several attempts, it gave up. So the real question is not how do I remove this error? The real question is why Abaqus unable to converge this increment? To understand this error, we need to understand how Abaqus solves nonlinear problems. Abaqus does not fully apply the full load at once. Instead, it divides the problem into small increments. Each increment applies a small amount of load or displacement, and inside each increment, Abaqus uses the Newton-Raphson method to find equilibrium. So in a nutshell, the process is apply a small load increment, iterate until equilibrium is reached, move to the next increment, repeat until the total load or total time is reached. Take a look at this rough diagram, and what we have here, total step time, and we have initial increment on the left hand side, and which is number 1, and we have the end increment. So by default, Abaqus uses 5 increments for the problem. Each line represents an increment. The distance or the size between two increments is the increment size, and the minimum increment size is the lowest size between the two, and the maximum is the highest. And here's the key idea. The Newton-Raphson method assumes that the problem is smooth enough inside each increment. If the response suddenly becomes highly nonlinear, unstable, or physically unrealistic, the solver cannot find equilibrium, no matter how small the increment becomes. And when Abaqus reaches the maximum number of cutbacks, it throws the error "too many attempts made for this increment." Now let's talk about the real causes. In practice, this error almost always comes from one of these reasons. Number 1, the load or displacement applied too aggressively. This is one of the number 1 causes, and by solving this, you can solve the "too many attempt" error. If you apply a large force or a large displacement or whatever it is, or steep amplitude, Abaqus is forced to jump too far in one increment, even if the total load is reasonable. How fast you apply it, it matters. Number 2 can be related to severe nonlinearity, so nonlinear problems are sensitive. Typical examples can be plasticity with sharp yielding, like tensile test, damage initiation or element deletion, buckling or snap through, contact opening and closing. At some point, the stiffness matrix changes too abruptly and Newton-Raphson fails. One of the most important one is contact issues. Bad contact definition causes convergence nightmares. For example, initial over closure, hard contact with no stabilization, too much friction, contact suddenly activating in one increment. So Abaqus tries to resolve contact forces instantly and fails. And another one can be the meshing or element choice. Highly distorted elements, wrong element types, or very coarse meshes in nonlinear zones can prevent convergence completely. Last but not least, unrealistic boundary conditions. Over-constrained models, conflicting boundary conditions, or rigid constraints can lock the structure and make equilibrium impossible. Now that you know where these errors come from, let's talk about how actually we can fix them. One of the most common ways to resolve this issue is to change the number of cutbacks. So first we need to go to the step, and from step you need to go to the other and general solution controls, and let's go to the manager, and we have a step 1. We click on edit, there's a warning, we ignore that, continue, and here we need to go to specify. And if we go here to the time incrementation, and if we go to more, you see here is the default numbers of cutbacks, and by default it is on 5. And if we change this number to a high value number, for instance 30, and we click on OK and we run the job once more, we see it can resolve our issue. The second way to do that is to go to the load, and instead of applying the load instantly, creating one amplitude. So in the load here we have, for instance here we have the boundary conditions, and in the boundary conditions and second step, which is the step 1 after step initial, we have amplitude here. We can create an amplitude here. For instance, creating an amplitude, it can be tabular. We can have the frequency, for instance 0, 0, 0.1, 0.1, 0.2, and it goes on to the number of steps. If the step 1 is step 1, all the way to the number 1 here, so 0.1, 0.2, 0.3, up to the number of steps, and click OK. So by this one you apply the load smoothly and it will be okay. So the next one is for the problems that involves contacts. If you go to the mesh here, as you see here, some elements are distorted here, but it's not really badly distorted. You have the weld here, or another thing that in contacts with another material, and the elements adjacent to it should be matched together like this. And you can reduce the mesh size, especially in the contact zone, and avoid any distortion, especially in these zones. And you have to go to the interaction here and make sure to create a good contact between the two, so it can be either surface to surface contact or general contact. And it's better to have a material properties for the contact here. If it's tangential behavior and there's a friction with penalty, make sure this friction coefficient is the correct value. Last but not least, if you've done everything and still you got the error, you have to change the step. So here I'm working with this cantilever beam and the step is static general. You can simply replace that with dynamic explicit. It means problem cannot be solved with static general because the deformation is really high, and with all those cutbacks, meshing, stuff like that, it can't be solved. So you need to shift it to dynamic explicit. Make sure that the NLGeom is on, especially when you have the nonlinearity, either in static general or dynamic explicit, and you can fix the incrementation, mass scaling, and everything else. And that's it for today. I hope you can resolve your problem using all these techniques I showed you. If you want to learn Abaqus better, click on the video on screen before it ends, and I see you there. Stay tuned.